SasquachIsReal, and this project will be exploring the natural convection from heating and cooling fins. Buckle up, you're in for a ride. Hopefully right now you're having vivid flashbacks to sitting in heat transfer class while Dr. Amin is saying, "Mechanical engineers, the best of the best," for the 10th time that week. Heating fins are devices that rely largely on natural convection to carry hot air up and away from the heat source. As you see, they can vary from simple to very complex arrangements depending on the requirements of the system. For this project, I sought to quantify whether more fins enhances this natural convection. In order to do this in a reasonable amount of time in MATLAB, several simplifications were made to the system. These simplifications were: assume rectangular fins, assume constant temperature in the fins, assume no heat transfer from the base that the fins are attached to, because we are interested only in the effect of adding more fins. Analyze only natural or free convection. Analyze two-dimensional domain. And analyze 3 separate cases. Also note that I used fins at 400 Kelvin and a fluid at 300 Kelvin. The governing equations used were those for 2D free convection of ideal gases. The necessary equations were continuity, momentum, and the energy equation, which are shown on this slide. For the discretization, I used central finite differences on all derivatives. Since there is no time derivative, these were all solved implicitly for 5,000 iterations. One challenge of this problem was enforcing the conditions necessary for the fin. In order to accomplish this, I created a function with the fin location that enforced a constant temperature and 0 velocity at all locations. All other boundary conditions were Newman conditions with the derivative normal to the surface set to 0. At this point you may be thinking like, wow, this is such an easy problem. But hold on to your horses for just a second there, cowboy. There was one major complication. As you see in the figure, the domain consists of 2 regions that represent different heat transfer problems. The bottom is a vertical plate free convection problem, where the top is a free convection without a source. To overcome this, I first solved for the bottom half of the domain, then passed that temperature to the top half to use as a constant surface temperature condition on the bottom of the domain. This slowed down the code a little bit, but it made the results much more accurate. Since all 3 equations are very coupled with each other, I chose to use the following solution method, shown here on this slide. Solve for the temperature at all bottom half interior points using the energy equation and force fin temperature requirements. Use this temperature to solve for temperature at all upper half interior points. Solve for U component of velocity at all interior points. Enforce fin vertical velocity requirements. Solve for V component of velocity at all interior points. Enforce fin horizontal velocity requirements. Apply other boundary conditions to velocity and temperature, and iterate many times. Here are some cool little videos of the temperature in the domain of the 3 cases. Here is the solution for 1 fin after 5,000 iterations. And here's the solution for 2 fins after 5,000 iterations. And for 3 fins after 5,000 iterations. Please note on all these solutions, there is a sharp discontinuity in the curve between the 2 domains. So how did the cases compare? As you can see in these plots, as more fins were added, the average vertical velocity of the domain and the average temperature in the domain grew quicker, confirming this hypothesis.